So today we're going to talk about multivariate random variables. So I've talked a lot about bivariate random variables, and we're going to kind of extend that to the case where we have more than two random variables at a time. And we're going to move pretty quickly through this lecture because this material is pretty much stuff we've already seen, but we're just going to extend it slightly and make the kind of hopefully straightforward generalizations of the bivariate case that we've seen. So if we have a set of random variables, x1, let's say to x sub n, if these are random variables, then we're going to define x with a tilde under it to be the vector of x1 to x sub n, either as a column vector or we can write it as a row vector transpose. This is x1 to x sub n. And we're going to put a prime here for transpose. And so this thing is called a multivariable random variable. I guess the correct word is multivariate random variable, or a random vector. So I'll probably stick with multivariate random variable, but they're also called random vectors for obvious reasons. They're kind of a vector of random variables. And we can go through kind of our standard definitions that we had for a univariate random variable and then for our bivariate random variables. And if, well, let's say we're going to define and PMFs and PDFs for multivariate random variables. And if the x sub i's are discrete, then what we're going to call the joint PMF. So we're going to use the same word as in the bivariate case, but now it's multiple random variables. We call it the joint PMF, is f of x tilde. So here x tilde is x1 to x sub n, and this is a number in Rn, is, so we can expand this out, it's fx1 comma, fx2 comma, all the way fxn. So you can write it either way. It's a multivariable function. This is defined as the probability that x1 is little x1 and x2 is little x2. Let's move this out of the way. And x3 is little x3 all the way up to x sub n is little xn. And so f in this case is a function from Rn to R. And it is called the joint PMF of the x sub i's. So this is the case if we have discrete random variables, if they're all discrete. The other case, so continuous case, is that if the x sub I are continuous, that is kind of marginally they're continuous, then the joint PDF now, so the same terminology as in the bivariate case, but now we just have multiple random variables, let's say is defined as it's some function, again it's a function Rn to R, so that if I have any A that is a subset of Rn, then we can get the probability, and what we could write here is that x tilde is an A. So we now have a multivariable random variable. This is the same thing as saying that probability that well, we could expand it as x1 comma x2 all the way up to x sub n, that this thing is in this set A. Our definition of our joint PDF is that to get that probability, what we do is we integrate our function f of x1, x2, x3 all the way up to x sub n. We integrate it over A, and this is now really a, so I can write, for example, x tilde, but what I really mean here is this is some multiple integral over whatever the bounds are that define A. So there's n integrals here, and it's f x1, x2, it's an n variable function, and it's dx1, dx2, etc., dxn. So this should all look kind of pretty familiar. As in the bivariate case, it's just now we have n variables at the time, but it's not a lot more complicated. We can define things like expectation. So this won't be too surprising, given that we've done this in the univariate and now the bivariate case. If I have some function g that goes Rn to R, then I could look at the expected value of g of x tilde. So recall here, x under tilde is just my vector of random variables. So x1 to xn, say transpose, we'll treat it as a column vector. And in this case, our expected value of g of x has, well, two cases. If it is a multivariate discrete case, or multivariate discrete random variable, or a multivariate continuous random variable, we get two different answers. In the discrete case, what we do is we sum over x1 and the sum over x2, etc., all the way to the sum over xn. What we're going to sum is g of x1 to xn. Let's move this out of the way a little bit, times f of x1 to xn. So this is for my case for my discrete. So it looks a lot like the bivariate case where we had the sum over x and y, but now we have a sum over x1, x2, x3, all the way up to xn. In the continuous case, it's kind of replace the sums with integrals. It's the integral of g x1 to xn times f, to move this, x1 to xn, dx1 to xn. And this is the continuous case. We can also define things for multivariable random variables, as we did in the discrete case. We have a theorem. Well, we can state it as a theorem. We're not going to go through and prove it. Marginal distributions. In the bivariate case, if we had the joint of x and y and we wanted the marginal of x, we'd integrate out y. In this case, now we have n different random variables, and we can get the marginal of any of them. The marginal PMF or PDF of x sub I is, well, we have two cases. F, and we're going to say x sub I of x sub I, is in the discrete case, we're just going to sum over x1, x2, all the way up to summing over x sub I minus 1. We're going to skip x sub I, sum over x sub I plus 1, all the way up to summing over x sub n. And we're just going to sum up the PDF, x1, x2, all the way up to x sub n. So in the discrete case, if we wanted the marginal of x, we would sum over y. If we want now the marginal of x sub I, we sum over all the other. So sum over all other. And in the continuous case, this is going to be a bunch of integrals, and we're going to integrate our joint PDF, and we're going to integrate now over dx1 all the way to dxi minus 1, skip dxi plus 1, all the way to dxn. So we're going to integrate over all the variables except the one that we want to get the marginal of. And that's very analogous to the bivariate case where we integrate or sum over the other variable. Now it's all the other variables. We can also talk about conditional distributions. And for the bivariate case, we get the conditional of x given y, or y given x. In this case, we can get the conditional of any of subset given any other subset. So if, let's say we have two sequences of indices, that's two sets of indexes, I1 to IM and J1 to J, let's say K. So these are just some numbers. Maybe it's 1, 3, and 5 in the first set, and 7, 11, and 12 in the next set. Okay. Whatever indices we choose of the x of i's, the conditional PMF or PDF, or discrete or continuous case, of xi1 to xim given, so the conditional distribution of these x sub i1 to x sub im, given that we have observed xj1 to xj sub k is, so the notation here is f of xi1 to xim bar xj1 to xjk. And as in the previous case, what we're going to define this as is it's the joint of all of the things we consider. So x sub i1 to x sub im joint with x sub j1 to x sub jk. It's supposed to be a 1 there. And then we divide through by the stuff we're conditioning on. So we're going to divide through by the joint of xj1 to xj sub k. And in the bivariate case, it would just x given y is a joint of x and y over the, say, marginal of y. So this is just a generalization of that whole fact. We can choose any subsets and condition on any other subset. And this formula kind of gives us, in the kind of straightforward way, what we would think of as the conditional PDF. Okay, so let's look at some examples of all this. So basically, I've just been extending all of our definitions in kind of the most natural way from one variable to multivariables. So we can look at some concrete examples of this. So first of all, let's consider 4 random variables, x1 to x4, with a joint, and we're going to say they're continuous, so they're going to have a joint PDF of, so our joint PDF is a 4-variable function, takes in little x1, little x2, little x3, and little x4, and it spits out the density, the joint density of all these things at that point. And we're going to say that it follows this formula. 3/4 of x1 squared plus x2 squared plus x3, 2 there. That's x3 squared plus x4 squared. And it's defined, or it's non-zero, as long as each of these x sub i's are between 0 and 1. Otherwise, we're going to say the thing is 0. Okay, so let's look at what we can do with this. First of all, we could ask a question. Say, what's the probability that x1 is less than, x1 is less than 1/2, x sub 2 is less than 3/4, and x sub 4 is greater than 1/2. That's a question that could be asked. We have now jointly 4 random variables, and we know the joint, in this case, P df is this thing, and our definition says we just need to integrate over this joint PDF over the relevant area. So it's going to be, we have 4 random variables, so it can be 4 integrals. We want x1 between 0 and 1/2. So 0 and 1/2. And we're integrating 3/4, our joint PDF, x1 squared plus x2 squared plus x3 squared plus x4 squared. And so that is the x1 limits. We want x2 to be less than 3/4, so 0 and 3/4. Why 0? Remember that each of them only has a non-zero density between 0 and 1. So that's dx2. And what's our last condition? x4 is between, see, dx4 is greater than 1/2, so that will go 1/2 to 1. Now I wrote a 4th integral. What's the last thing? Well, I need my limits on x3 or anything. So x3 can be anywhere between 0 and 1. So those are my limits for x3. At this point, it's just going to be a calculus problem. And I'll give you the answer. So I'll say calc 3. It's not a particularly hard calc 3 problem. It's just since you can break out this integral. You'll get about 3 over 256. That should be the answer. But at this point, once you set up the problem, you're 90% of the way there. You just have to do the integral. But so this is, how our joint PDF is useful. You can calculate probabilities by integrating it over the proper area. So in the univariate case, you'd integrate over the section of the real line you want to find the probability of. In the bivariate case, you'd integrate over the plane, and now it's just, well, in this case, we're integrating over a 4-dimensional space. Other questions we could ask, we could say, what is the joint distribution of x1 and x2? So if I want the joint distribution of x1 and x2, I just have to integrate out x3 and x4. So f of x1 and x2 is integral of f of x1, 2, 3, 4. So it's the joint of all 4 of them, and I'm going to integrate out x3 and take the second integral with respect to x4. And my limits of integration are 0 to 1, right? We know from our definition that each of the random variables sits between 0 and 1. And recall that this joint thing is 3/4 x1 squared plus x2 squared plus x3 squared plus x4 squared. So again, I'll leave the calc 3 up to y'all, and you can do this integral. Because we're only integrating now with respect to x3 and x4, we're going to get something that depends on x1 and x2. And if you do this integral, it comes out to 1/2 plus 3/4 x1 squared plus x2 squared. So that is my joint of x1 and x2, right? And not surprisingly, it depends on x1 and x2, but not x3 and x4. We've integrated those out, and so we no longer kind of have that dependence. We could use something like this. So part C would be, what is the expected value of x1, x2? Now we're just actually back in the bivariate case. And we've seen how to do these, right? I want this. How do I calculate my expectation? Well, I'd integrate my function, which is x1 times x2, and then I'd integrate my joint PDF of x1 and x2, which is 1/2, plus 3/4 x1 squared plus x2 squared. And I'm integrating with respect to x1 and x2, and my limits of integration are 0 to 1 for both. And I'm giving you a lot of Calc 3 homework today, but Calc 3 gives you 5/16 as your answer. That's the expected value of x1, x2. Cool. Notice you could have calculated this directly. You didn't have to get the marginal first. You could have just integrated the joint of all of them over x1, 2, 3, and 4. You'll get the same thing because you'll first do the integrals, say, with respect to 3 and 4, which will get you this value of 1/2, 3/4, etc. Then you multiply by x1, x2 and do the rest. Anyways, you can think about why it doesn't matter which way you do it. And as a last little follow-on for this example, we could say, what is the conditional distribution of, what do we want to look at in this case? x3 and x4 given x1 and x2. And from our definition, if we want f of x3 and 4 given, so bar, x1 and x2, so what is the density of x3 and x4 if I know the values? Little x1 is little x1 and x2 is little x2. Our definition was that this is the joint of all of them over the marginal of x1 and x2. And so we kind of know all these parts at this point. The top, the joint of all of them, is 3/4 x1 squared plus x2 squared plus x3 squared plus x4 squared. And the bottom is our joint of x1 and x2, or the marginal of x1 and x2, which we said was 1/2 plus 3/4 x1 squared plus x2 squared. And so this is the conditional of x3 and 4 given 1 and 2. Okay, that's a nice little starter example of some of this in practice with 4, but random variables, and we haven't seen that many at a time before, and you can think about how you could extend this generally to multiple random variables. Okay, so what are some other concepts that we talked about in the case of bivariate random variables that we now extend to our multivariate random variable situation? The first is mutual independence. So as we saw with events, we talked about independence of events, and then we talked about independence of multiple events. We call it mutual independence. You can have mutual independence of random variables. So we say that our collection x1, x2, x3, all the way up to x sub n, are mutually independent. And we typically drop the word mutually, but you can think about it for now if you want. They're independent of each other. And the way that we think about this is, so the technical definition, which is not particularly useful, is that if we say these things are mutually independent if probability of x1 in A1, x2 in A2, x3 in A3, all the way up to x sub n in an. So let's say we're going to have some sets A1 to AN. They're sets of real numbers. The probability that x1 is an A1, x2 is an A2, x3 is an A3, etc. And I should add in a qualifier here, if for any subsets of the real line, if we can factor this as the probability that x1 is in A1 times the probability of x2 is in A2, etc., times the probability xn is in AN, then, well, I can just put a period, right? So the statement is, we say that these x sub n, x1 to xn, are mutually independent if for any sets a1 to an, that are subsets of the real numbers, the probability x1 is an a1, x2 is an a3, x3 is an a3, etc., is the product x1 is A1 times x2 is A2, etc. Right? So I can write out this product. I can do this factorization. We say the random variables are mutually independent if I can do this for any sets. Now, that's the definition. It's not the most useful definition. Practically, when we want to calculate things. So here are our theorems. So we're going to say our collection, so I'm going to write it like this, our collection of these x sub i's are independent. I'm going to drop the word mutually here. Are independent if and only if A, if I look at the joint distribution of all these, joint PMF or PDF, if I can factor that as the product of the marginals. So say fx1 of x1 times fx2 of x2, etc., times fxn of xn. So if they're mutually independent, I can factor the joint as the product of the marginals, or if I can factor the joint as the product of the marginals, they're definitely independent. The same thing can be said with the CDF, which we didn't really define the joint CDF, but you could imagine it's going to have a pretty straightforward definition, just kind of generalization. We could also do this, that the joint CDF, which is just the probability that they're all less than or equal to than their respective values, is if we can factor that thing as the product of the marginal CDFs, that's an equivalent characterization of independence. So that's the more practically useful thing. And typically we use A. We typically don't tend to talk a lot about joint CDFs. The other useful theorem, which we saw in the bivariate case and can be extended to the multivariate case, is that if we have a collection of x sub I that, let's say, if these x sub I are independent, and g sub I is just some real valued function, so we can have a real valued function associated with each of them, then the expected value of gi, or let's say it this way, of g1 of x1 times g2 of x2 times gn of xn, we can factor this. So we can actually distribute the expected value over product if they're mutually independent. And so we saw we could do that in the bivariate case, and a generalization holds in the multivariate case, where if they're independent, and then I can write expected values product as the product of the expected values. And the corollary here, so there are kind of two corollaries. Corollary is that the gi of xi, this collection, are independent. So you could think of, instead of working with x sub i's, I could transform each of the x sub i's into some gi of x sub I, call it y sub I if you want. Those are all actually independent, right? And we saw the same thing in the bivariate case, where if I had a function of x and a function of y, if x and y are independent, then the function of x and the function of y are also independent. That's just generalization of the same thing. This also gives us some nice theorems. So here's another corollary about MGFs. So MGF of sum of independent. And we know that MGFs are defined as expected values. So this got a theorem above something to say about MGFs. If my x sub I are independent, and let us define z as the sum of these x sub I. So z is a function of the x, all the x sub i's. It's the function that sums them together. Then the moment generating function of z, of the sum of them, at some value t, is the product of the moment generating function of each of them. So the proof of this is actually straightforward enough. We can kind of write it in one line. Moment generating function of z at t is the expected value of e to the t. Let's write little z, so I'll write it like that. E to the, oh no, I want a capital Z, don't I? Right? E to the tc. Back up here, right? And z has the definition of the sum of the x sub I. So let's just plug that in. Expected value, the sum of these x sub I. And we can use our properties of exponents to say that this is the product, I goes 1 to n, of e to the t x sub I. And if the x sub I are independent, then our g sub I of x sub I is e to the t x sub I. And these are all independent, and so we can distribute this expected value through the product. This is, so we can go like this. And of course, this is m. This is the moment generating of x sub I at t. So that completes the proof. And that shows that the moment generating function of the sum is the product of the moment generating function of all the individual random variables, under the assumption that must be true, which is that they're independent. So another follow-on theorem, which I'm not going to prove because I think it's probably, well, I'll leave it up to you. It's not so bad. You can think about what the proof might be, is that if a sub I and b sub I are constants, so we have a sub 1 to a sub n, b sub 1 to b sub n. I could slightly extend this and say z is the sum, I goes 1 to n, of, instead of the x sub I, it's ai plus bi xi. And you can think about what the MGF would be. The answer is that the MGF is e to the t times the sum of the b sub I times the product of the MGFs of the x sub i's. Now, instead of at t, they're at, a sub I t. And this is very similar to a theorem we saw back for the univariate, back in the nice simple univariate world, where we looked at linear MGFs of linear functions of random variables. And we got something kind of reminiscent there. So an example of where we could use this is that if we have some x sub i's, and each of these x sub i's has a normal distribution with a mean mu sub I and a variance sigma I squared. So now all of these x sub I, we're going to say the x sub I are independent, but they all have different means, mu sub I, and they all have different variances, sigma I squared. Then if I look at the sum, let's say of ai plus bi x sub I, this sum is going to have a normal distribution, is also going to be normally distributed. So you can call this thing y if it makes you happier. It's some univariate random variable, all right? And I'm summing up all the x sub i's and multiplying them by a constant, adding on another constant. That's just some univariate random variable, and it will have a normal distribution, and its mean will be the sum of the means, which is ai mu I plus b. Oh, I wrote this the wrong way, right? It's bi mu I plus ai, and the variances will be sum of bi squared sigma I squared. So I've kind of claimed this. How to show, use previous theorem. We've kind of showed this in the previous cases, but now it's just a little more complicated because now we have a bunch of normals, but you can show that the MGF of the sum of normals, if they're independent, is, again, the sum of normals. So I'll leave that as an exercise, but that's one way you can show that sum of normals kind of gives us another normal distribution. Okay. So we've done a lot of things with bivariate transformations, and in particular, one thing we had looked at, we talked a lot about, was transformations of bivariate random variables. So let's look at how we can now go from bivariate transformations to multivariate transformations. And it's actually not that bad. Again, it's just like everything we see in this lecture. It's just a slight generalization of the stuff we've seen before. So it's just that little bit. There's a big jump from univariate to bivariate, and then a smaller jump from bivariate to multivariate. So multivariate transformations. And the reason we'll see very much next time is I'll give you a little bit of a taste of what 452 would be like next time. And its statistics is all about functions of random variables. We call those functions statistics. And so things like multivariate random variables is all you talk about there. And transforming things, finding functions of these multivariate random variables, is all you do, because those functions are what we call statistics. Okay. So let us consider a function g, and g, my favorite letter for function, is a function from Rn to Rn. So it takes in a vector in Rn, it spits us out a vector in Rn. And let's say x tilde, which is x1 to xn, is a random vector. We're going to define a new random vector, u, to be g of x. So another way of thinking of that is that, i.e., u will have n components, and the ith component of u is the ith component function of g applied to x1 to xn. So here gi is a function from Rn to R, is the ith component function of the whole transformation g. But so overall, we're doing is transforming from an n-dimensional random vector to another n-dimensional random vector. And the theorem, we're just going to focus on one theorem. In the continuous case, if g is invertible and differentiable. So G is an n-dimensional function, Rn to Rn. It must be invertible and must be differentiable. You can think about what that means in an n-dimensional case. It's a little more complicated than just the univariate case. But if those things are true, then we can get the PDF, the joint PDF of U. This is a joint, so I say joint PDF because U has self as an n-dimensional random vector. It is, if I take the joint PDF of X and evaluate it at G inverse of U, and I multiply by the absolute value of the determinant of the Jacobian matrix of the inverse. So derivative of G inverse with respect to U. So I'll write it like that. So here, dG inverse du is the n by n matrix, where the first row is dG1 inverse, du1, dG1 inverse, du1, du2, all the way up to dG1 inverse, dun. And then the second row starts dG2 inverse, du1, etc., all the way down to the last entry will be dGn inverse, dun. Okay. So now, in our multivariate case, this is our Jacobian matrix, which is an n by n matrix, so it's n times n. It will have a determinant, which may be easy or difficult to find. And you can take the absolute value of that determinant of that Jacobian matrix, and you multiply by the joint PDF of my original variables, and evaluate that the inverse function of my new set of random variables. So we can look at an example, and generally you can make this as complicated as you want, but we'll look at one where we can actually get a nice little solution. So here's going to be my setup. Here's my example. And we're going to let x, the x of I, and I can write it like this, iid exponential lambda. So this notation here, iid is independent and identically distributed. So all of the x of I are independent of each other, and they have an identical distribution, that is, namely in this case, exponential distribution with lambda. Okay, we want to look at a transformation of these. So let's define a transformation so that so U is G of our x, right? And we can define it component-wise. Specifically, we're going to say that U1 is x1, U2 is x1 plus x2, U3 is x1 plus x2 plus x3, etc., all the way up to U sub n is x1 plus, etc., all the way up to x sub n. So it's the sum of all of them. Okay. So I can define my u's this way, which is kind of the various partial sums of my x's. x1, x1 plus x2, x1 plus x2 plus x3, etc. I want to get the joint distribution of my u's, as defined here. So how do I do this, right? First, we need to get the inverse transformation. So I want to get the x's in terms of the u's. Well, x1 is easy to get. x1 is just u1. So this is g1 inverse of the u's. It's just u1. So here I'm using u as a shorthand for u1 to un. Okay. x2, if I subtract u2 from, or u1 from u2, I just get left with x2. This is x1 plus x2 minus x1. So this is u2 minus u1. So this is g2 inverse of the u's. And I can continue playing this game. If I want x3, I could take u3 and subtract off u2. That would give me back x3. So this would be my third component of my inverse function. And all the way down, something similar to x sub n, which is u sub n minus u sub n minus 1. So that would be the nth component of my inverse function. So un inverse of, or sorry, gn inverse of the u. So these are my inverse, or together, these define my inverse transformation, G inverse. And I have to now get my Jacobian matrix. So remember that if I call J, let's say J is my Jacobian matrix, is the derivative of the inverse with respect to these u's. So this is an n by n matrix now. J, the ijth component of this is the ith inverse function, derivative of that with respect to u sub j. So that's another way of defining what my Jacobian matrix is. And so if I look at my inverse functions, say if I would to look at, well, let's look at what this J matrix looks like. Okay, so it's some n by n matrix, and we'll spot the pattern pretty quick. Okay, so the first row of my Jacobian matrix here is going to be the derivative of all of the different inverse functions with respect to u1. Well, if I look at my inverse functions, okay, derivative of the first one, g1 inverse, with respect to u1, is 1. So I'll get a 1. Derivative of the second one, which is this one, I will get a negative 1. Actually, no, which goes here, right? Because, sorry, so the first row, let's back up here. The first column here is the derivative, right? So as I change I, it's the derivative of all my inverse functions with respect to u1. So I'm at not the first row, the first column. So we get 1, I get negative 1. Then the next entry in that first column will be the derivative of my third inverse function with respect to u1. Doesn't show up anywhere, so it's 0. In fact, the u1 shows up nowhere else, so the rest of those are zeros. Okay, what's the second column going to look like? The second column is the derivative of all my inverse functions with respect to u2. u2 doesn't show up in the first one, so I get a 0. It shows up in the second inverse function, g2 inverse of u, and I'll get a 1. And it shows up in the third one, and I'll get a negative 1. And then the rest of this will be zeros because it doesn't show up anywhere else. And in fact, if you complete the pattern, what you're going to get is you're going to get 1s on your main diagonal, and you're going to get negative 1s below the main diagonal. And you're going to get 0 everywhere else if you take the derivative of all those functions. And so in general, the determinant, so eventually we need to find the determinant of this thing, right? We want determinant of my Jacobian. The determinant of a general n by n matrix can take quite a bit of time to compute. In this case, it's a diagonal, and so it's just the product of the diagonal because J is not a diagonal, it's a triangular matrix. So if you remember from linear algebra, the determinants of triangular matrices are just the product of the main diagonal. And the product of this is 1 times 1 times 1 times 1 times 1. And so the absolute value of the determinant is also 1. Let's just say the determinant is product of diagonal entries. So actually, in this case, the determinant goes away in our calculation. If we go back up to our theorem, right? It's going to be, we're multiplying by this determinant of the Jacobian absolute value. Well, that thing goes away in this case. So in this case, what we get is that our joint of the u's is the joint of the x's evaluated at the inverse function of the u's. Okay, so what is, first of all, we need to figure out what's the joint of the x's. We kind of know piecewise what G inverse looks like. We found all those before, so those are these things up here. So recall that my x sub i's are independent, identically distributed with an exponential function. We haven't, or exponential distribution. We haven't used this fact yet. This says, what does it say? It says that if I look at the joint distribution, so I'm writing this as f of x under tilde. That's just shorthand for fx 1, 2, 3 to n. Because they're independent, I can just write this as the product of the marginals. So this equality here comes because independence of the x sub i's. And not only are they independent, but they have the same distribution. And so the marginals are all the same. So that's what we mean. That's the ID in the part of IID. Independent, the first I, identically distributed, the second part. So they all have the same marginal. Let's just write f of x sub I. And this f here is the PDF of an exponential. Oh, let's write this legibly. It's the PDF of an exponential lambda. That is f of x here is lambda e to the negative lambda x, as long as the x's are positive. And so this is lambda e to the negative lambda x sub I when we plug it in. And we can actually simplify this. We can, what can we do? We can at least pull out a lambda to the n. Yeah, and actually we can pull out lambda to the n, and then this is product goes 1 to n of e to the negative lambda x sub I. Okay, so why are we getting this, right? In our formula here, we needed the joint of the x's. So this is this f sub x here. We can write sub x. And we know now, we know what all the inverses are. We know what fx is, so we can say that the joint of the u's, we get by taking the joint of the x's and we plug in the inverse. The inverses are, the first inverse is just u1. The second inverse is u2 minus u1. Then it's u3 minus u2. Then it's u4 minus u3, etc., all the way up to u sub n minus u sub n minus 1. All right, so we derived that above. And now we can plug in what f is, and we can plug each of these into f x tilde. And what do we get? So it's the lambda to the n out front. And we'll get e to the negative lambda, and now instead of x sub 1, we write u1. E to the, instead of x lambda x2, it's lambda u2 minus u1, etc. And we'll get all of this, so we'll just do run one more. And then it's e to the lambda, instead of x sub 3, it's u3 minus u2. So it's plugging in the inverse functions. Dot, dot, dot. E to the lambda u sub n minus u sub n minus 1. And what we'll notice is that we can add the exponents. And if we add all these exponents, what are we going to be left with? Well, the lambda u1, negative lambda u1 will cancel with the lambda oops, there should be a negative sign out in front of each of these, right? It should be negative, 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 right? There we go. Okay, so that negative lambda u1 is canceled with negative, negative lambda u1. So we're left with the lambda to n, and the negative lambda u2 will cancel with the negative, negative lambda u2 here. And so we're going to get a bunch of cancellations. And all we're going to be left with at the end of the day is everything's going to cancel except a negative lambda to the u sub n. All of the other exponents are going to cancel with each other. We could just add them all together, right? Because if we expand out exponents, we can add them since we have a product of exponentials. What we're going to get is negative lambda u1 minus lambda u2 plus lambda u1 minus lambda u3 plus lambda u2, etc. So we're going to get the negative lambda u1 cancels the lambda u1, negative lambda u2 cancels with the lambda, that should be a plus, lambda u2, etc. And we're going to cancel all these. And all we're going to be left with is at the end of the day, is a negative lambda u sub n. So that partially answers, that fully kind of answers the question, which is that the joint distribution of the u's is lambda to the n, e to the negative lambda u sub n. So that's my joint distribution of the u's. And this is true. So it's interesting that the joint distribution of the u's only depends on the last one. Kinda. There's a condition that this is true. What has to be true about these? This is true as long as we have a certain order. Oops. Is that u1 is between 0 and u2, u2 is between u1 and u3, etc. So all of these ui's have to be ordered. Why? If we go back up to our definition of u1 is x1, u2 is x1 plus x2. So x1 plus x2, both x1 and x2 are positive. That better be bigger than, so recall u1 is x1. That better be less than x1 plus x2, since everything's positive here, and that's u2. So u1 better be less than u2. And you can play that game with all of these. u2 better be less than u3, u3 less than u4. So the other u sub i's don't show up in the PDF, but they show up in the condition defining where the PDF is non-zero. Everywhere else, this PDF is 0. They have to maintain this ordering, otherwise it's not really a valid set of u sub i's. The u sub i's have to kind of be in increasing order. So that is our kind of example of our joint distribution. Okay. So to kind of close out today, what we're going to look at is we're going to look at some kind of nice linear algebra and generalizing means and variances. So let's do that. So let's say means slash variance in multivariable case. So to back up real quick, in the univariate case, that's not very legible, is it? Univariate case, we could say, like, you know, expected value of x is some number, some real value number, and the variance of x had this nice formula, its expected value of x minus its expected value, square that whole thing. That's also just some number. are there similar concepts for the multivariate random variables? And there are. For multivariate, we now get, instead of expected value being a number, expected value of a random vector, or x tilde. So x tilde, again, is my notation for my random vector x1 to xn. I'm thinking of it as a column vector. This we can define just component-wise. It's just the vector of expected values of the various marginal random variables. Expected value of x1, expected value of x2, and expected value of xn. And so now, instead of being a real number, it's a n-dimensional mean vector. Sometimes people will call this mu. So mu, or the mean, is now a point in n-dimensional space. Similarly, so this is expected value. We can, instead of having a variance, in the univariate case, we had this nice notion of variance. Now, we talked about this a little bit, we have the covariance matrix. So while means scale from just being a number to a vector, variances scale from being a number to a matrix. So you can either call it the covariance matrix or the variance covariance matrix. Either are acceptable. So we typically would denote COV as in covariance, and now we're going to do something weird. We're just going to give it a vector instead of giving it, normally we talk about covariance of x and y, but the notation is just a vector now. And typically this is denoted as a capital sigma. Let's write that legibly. Capital sigma. And this is going to be an n times n matrix. So it's a real n by n matrix. And it's defined, the entries, sigma sub ij, are going to be the covariance between x sub I and x sub j. Notice that this means that sigma sub I is the covariance of xi with itself, which is the univariate variance of x sub I. So it's the variance covariance matrix, or just often just shortened covariance matrix. The main diagonal gives us the variances, and the off diagonal entries give us the covariances. So an illustration, something like this. The main diagonal is variance of x1, variance of x2, etc. And the off diagonal is like covariance x1, x2, or covariance x2, x1. Notice that this matrix will be symmetric, which is a very important property of matrices. So if you take a kind of intermediate linear algebra, this property of symmetry is very important. And in this case, the variance covariance of the covariance matrix is a n by n symmetric matrix. Yeah, we'll leave it there. Okay, so we can define how do you, so that's one, this is one way. Another, so as kind of as a cute aside, another way of defining my covariance matrix, sigma, is the expected value of x minus its expected value times x tilde minus its expected value transpose. So this is a n by 1 vector. This is a 1 by n vector. And so the whole thing will be an n by n matrix. So expected value is kind of just element-wise of the matrix. And this is kind of similar to how you could define variance of a univariate x as the expected value of x minus its expectation times x minus its expectation. Typically, you write that squared, but you could say it's x minus its expectation times x minus its expectation. valid, and that's kind of the multivariate generalization. Well, now we're working with vectors instead of just numbers, so we need a transpose in there. But that will, so this is kind of a cute little side of another kind of, it shows that the covariance matrix is kind of a direct generalization of variance. So the role, the covariance matrix plays the role of variance in the univariate case. And so we already said that this covariance matrix is symmetric. We have some theorems about how covariance matrices behave. So let's just write out theorem. And that it's actually mostly pretty simple linear algebra. So I'm not going to go through all the proofs here, but you can think about why these are true. So let's say if A is a vector in Rm and B is a real valued matrix in M by N, and again, X tilde is a N component random vector, then we can look at, we can look at the expected value of A plus B X. So here, this thing here is a vector. It's a different random vector than X. It's a, you multiply by a matrix on the left and you add a constant A. That will give us another vector. Now it is in Rm. A plus bx is in Rm. And the theorem for expectation, that maybe is not too surprising. This is A plus, oh, sorry, it should be a capital B, shouldn't it, right? It's a capital B. It's A plus B expected value of X. And this is not too surprising. This is just basically linearity of expected value. You spend all linear algebra talking about how expectation, or how matrix multiplication is linear. And so it plays nicely with expected value in a kind of more general sense, because adding a vector or multiplying by a matrix are all linear operations, so they can just be factored, can kind of play nicely with expectation. And if I want to look at the covariance matrix of A plus B X, in the univariate case, I would be able to ignore additive shifts. I could ignore A, and you can in this case. It's going to be related to the covariance matrix of X, right? Remember, this thing is n by n. And the way we get the covariance of Ax plus B from the covariance of X is we multiply on the left by B and on the right by B transpose. That will give us a M by M matrix, which makes sense because this is an Rm, m-dimensional random vector now. A plus bx is kind of an m-dimensional random vector, and so its covariance matrix would be m by m. And so this is the formula. It's B covariance of x, B transpose. And so the analogy here in the univariate case, the analogy in the univariate case is that the expected value of A plus bx is A plus B expected value of x, and the variance of A plus bx is B squared variance of x. Well, now we don't have B squared. It's more complicated than when you're working with vectors, or random vectors, because now we have a matrix instead of just a single number, so it's kind of like B squared. We have a B out front, and we have a B out back. So it's kind of the matrix equivalent of squaring B. Okay. So let's see. So in the last kind of couple minutes, let's talk about the multivariate normal case. So the most famous multivariate distribution is called the multivariate normal, and this is one of the most important distributions, and it generalizes not only the univariate normal, but generalizes the bivariate normal. And we've talked about both of those. And this is something that is very important, not only for just statistics, but for a lot of kind of machine learning theory and just understanding how these things work. They're all based on kind of multivariate normal. So here we have our our random vector x1 to xn, and we say it's normal. And the notation is it has a mean vector mu and a covariance matrix sigma. So here mu is our mean vector, which is in Rn, and sigma is our covariance or variance covariance matrix, which is an n by n matrix. So it is like the univariate case where it's parameterized by a mean and a variance. This is parameterized by a mean vector and a variance covariance matrix, which are the generalizations of those univariate concepts. And the PDF, the joint PDF, if you want to think about it, of my multivariate normal. So here my x tilde here is just shorthand for x1 to xn. So it's some vector. It's just my vector notation for something in Rn. Some people put little hats over that. I put a tilde under it. The PDF has the following form. It's 2 pi, well, that shows up again, to the negative n over 2, determinant of sigma to the negative 1/2. That's so 2 pi to the negative n over 2 is like 1 over root 2 pi, but now we have a power of n because it's multivariate. Instead of having 1 over sigma, we have 1 over the square root of the determinant of the covariance. And we have an exponential of a negative 1/2, and it's x minus mu. Whoops, let's get this right. So it's a vector. This is all vectors now. X minus mu. And normally it would be negative 1/2 over sigma squared x minus mu squared, but we're going to write it like this. X minus mu, sigma inverse, x minus mu. So this is the PDF. Notice that this thing here is just a number. If you work out the dimensions, it's a n by 1 vector, or a 1 by n. I'm missing a transpose here. Let's work out the dimensions to get this right. It's x minus mu transpose sigma inverse x minus mu. Now it works out well, okay? It's a 1 by n times n by n times n by 1. So that gives us just a 1 by 1 matrix, which is a number. So the analogy for the univariate case was that my PDF, I could write it like this. 2 pi to the negative 1/2 sigma squared to the negative 1/2. So that's not, in the multivariate case, we have determinant of what the analogy is, the covariance matrix to the negative 1/2. And then I could write this as exponential negative 1/2 x minus mu sigma squared to the negative 1 x minus mu. So you don't write it that way in the univariate case, but you could. And when you write it that way, it makes very obvious that the multivariate version is some kind of direct generalization. But now we have to be a little more careful. We can't square a matrix, so we take, we can't say 1 over sigma squared. Well, you can't do that. You can invert a matrix and come up sigma inverse. So instead of sigma squared inverse, you have now capital sigma inverse. And instead of squaring something, you take x, instead of squaring x minus mu, it's x minus mu times sigma inverse, or x minus mu transpose times sigma inverse times x minus mu. Just a little more complicated because it's now using matrices. There are some special cases. If mu is the 0 vector, 0 in Rn, and my covariance matrix is the identity I sub n, then this is, we call the standard, I'm going to abbreviate this as MVN, multivariate normal distribution. So the standardized version of the multivariate normal is a zero mean vector and identity matrix as the covariance matrix. Some other kind of cute theorems. We can combine, so if you go back up, we had talked this theorem about how do we get the mean and the variance of a linear transformation, right? Of ax plus b is a linear transformation. Matrix multiplication is linear. If we have x is normal, it's multivariate normal with a mean mu and a covariance matrix sigma, so that's the notation. And a is m-dimensional vector and b is a n by m matrix. If, let's say, y tilde, sure, why not, is a plus b x tilde, so y tilde here is a m component random vector. So we transform the n component random vector x into a m component random vector y. And if x originally was multivariate normal, then y is also multivariate normal, but its mean is now a plus b mu, which we know from our theorem, and the variance we also get from that theorem is b, or the covariance matrix is b sigma b transpose. This is kind of a really nice theorem that says linear transformations. So getting the mean, the covariance matrix, are just applying our previous theorem. What this theorem is telling us is that linear transformations of multivariate normals are also multivariate normal. That doesn't have to be true, but it is. In fact, the kind of follow-up is that it's kind of a defining characteristic of the multivariate normal. So some random vector x tilde is multivariate normal if and only if, I'm going to write it like this, every linear combination of its components is linear. So beyond the scope of the course to prove that, the most useful is the forward direction, which is kind of what this theorem is telling us, which is that if I have a multivariate normal, I take a linear combination or a linear transformation of its components, that's also multivariate normal with the appropriate mean and variance covariance matrix. But actually, instead of defining the multivariate normal by its PDF, we could you could actually just say whatever random vector, if there is a random vector out there for which every linear combination of its components is multivariate normal, I didn't write this, every linear combination is normal, then our random variable is multivariate normal. So it's kind of like a characterization of multivariate normal. Some other useful corollaries are marginals of a multivariate normal are normal. And you kind of just pick off the right components of the mean vector and the covariance matrix. The caution is that if marginally the x sub I are normal, there's no guarantee, unless we know some other information, that jointly they are normal. So marginally, so if you have something that's multivariate normal, then its marginals are just univariate normal. if you don't know anything, it doesn't necessarily go the other way. If you don't know anything about the relationship between these, just because they're marginally normal doesn't mean they have to be jointly normal. Okay, so this is kind of a tour de force of multivariate random variables. So it's our kind of one lecture on it. It's very important, and we're going to have homework on it. But I think most things generalize in a pretty straightforward way, and kind of we have all the kind of same properties you saw in the bivariate case. Now it's just a couple more variables, my integral or my sum. We can start playing interacting linear algebra with probability in some really fun ways once you get to multivariate distributions. Okay, we're going to stop there for today.